Welcome to EE 597 with Professor Krishnamachari on Wednesday, June 22nd, 2016.
Okay, so let's resume from where we left off. So we've been talking about the link layer for wireless networks, and we started with the, oh sorry, can we have the overhead camera please? Yeah, thanks. So we started with looking at some problems of power control. Actually, before that even, power allocation over parallel channels. And you can really think of this as a resource allocation problem. And the example we gave was maybe for OFDM, and you have multiple users, and you're deciding how to allocate powers to those users. And you're trying to do, for example, sum rate maximization with constrained power. Right. And we looked at how you formulate this problem, how do you solve it, and there's a solution for it that we discussed that's called water filling. And for your homework assignments, you did a variant of this problem where you're trying to allocate not to maximize the sum of the rates, but actually to try and meet certain target rates as well as possible, right? And so then the solution wasn't quite water filling, it was a little different. But the broad class of problems had to do with power allocation over multiple parallel channels. So then we've looked at a problem of power control over independent links. And what I realized in looking back over the notes is that we covered the two-channel case and kind of left it at that. So I'm going to briefly go back to that problem and describe how do you generalize it to any number of links. And then we'll resume with the So we talked earlier about how it works for two links. Today we'll discuss sort of the generalization to any number of links. Okay, and then we'll go back to the other topics that we've been starting to talk about, which was slotted aloha and PCSMA. And then today really I want to get to talking about IEEE 802.11 CSMA, which when we analyze it will kind of reuse a lot of the analysis we did for PCSMA, but it has on top of that a finite state machine that is unique to the way CSMA does, 802.11 does CSMA. And so broadly these have to do with randomized channel access. So before I resume the randomized channel access topic, I want to go back to the problem of power control over independent links and talk about how that works for any number of links. So just to remind ourselves of what that problem was for two links. So what that looked like. So we had two sets of transmitter and receiver pairs. And these are like the forward channels for them. And here the assumption is that they are transmitting simultaneously, and because of that, and on the same channel, and because of that, they're interfering with each other. And we said that there's some gain in the forward channel and in these cross channels that's described as follows. And earlier we were talking about in the study of physical layer that these gains themselves could be time varying because of the wireless channel conditions. Here the assumption is that the gains are not are given or known, right, and not time varying and not varying. Okay, and this would be, for example, a reasonable assumption for slow fading environments. So in a slow fading environment, you have time to take measurements over a channel. You know what transmit power the sender sent a signal at. You can measure the receive power, and between those two, you can figure out what the gain of the channel is. And this information can then be sent back to the transmitter so that it's aware of the gain on that channel. And so the assumption in solving this problem is that we have measured all of the gains, and what we measured is correct. And that's reasonable so long as the gains are not changing dramatically over time, and that happens in slow fading environments. Again, just to refresh our memory about slow fading environments, these show up when there's not a lot of mobility. If the source is not moving, the receiver is not moving, nothing in the environment is changing. So we've taken measurements, for example, at our test bed here on campus, as well as at ISI, where we measure the quality of a link, the gain on a link, and all through the night it stays virtually constant. And all through the day it changes dramatically over time. And the reason for that is quite simply that during the day there are people walking around, there are other sources of interference, doors being open, microwaves being turned on. There's all kinds of dynamics that happens during the day. These are links in a static test bed, so the nodes themselves are not moving, but there's a lot of dynamics in the environment. So during the daytime, those links experience fast fading. But at night, when there's nobody in the offices, there's nobody actually moving around, there's no change in the multipath components. So whatever that gain is, it tends to more or less stay the same for 12 hours or so. In fact, people have used this idea to even try and detect the presence of humans by fluctuations in the RF environment. So that's sort of an indication that there is mobility in some sense in the environment. So, anyway, so for this problem, that's the assumption. And we said that really what we're trying to do is ensure that the SINR at both of the links is above some nominal threshold, right? And we said the SINR, for example, for link 1 would look like the transmit power at link 1 times G11 divided by, now the interference source would be P2 times G21 plus noise needs to be bigger than theta, or bigger than equal to, let's say, and P2 times G22 over P1 times G12 plus N is greater than equal to theta. So we had these equations, and then we derived that basically if you write these out by taking the denominator here, multiplying it out to the right-hand side and rewriting these equations, you basically have two linear inequalities. And the region we're looking for is the choice of P1 and P2 such that both inequalities are satisfied. And so long as certain conditions are met, we found there could be a solution for this, such that at these values of P1 and P2, both of these conditions hold, right? So if we want to generalize this to more than two links, all we have to do is to write similar equations, but in general for any number of links, right? So the general problem from what we had for two links kind of looks like this. So imagine not just two links, but any number of links. Okay. And we'll have some sets of transmitters here, sets of receivers here. And we have the forward gains on each of these links. So for example, if these are just numbered somehow, right? So if I take some arbitrary one over here, let's call it TXI, and some RXI. So the forward gain on it, let's call that GII. And there are all of these interfering links that we have. And so, for example, this one would have gain GI1, GI2, and so on. Right? And the same holds for all of these other transmitters as well. Okay? So we just generalize the problem where there's a whole bunch of links all trying to operate in the same region on the same channel at the same time. And the question is, can we somehow allocate power levels to all of these links so that we can operate all of them successfully? So in this setting, again, just like we had before, we're going to have to just write down all of the conditions where we want to say the SINR for the ith receiver is bigger than the desired threshold, and we want this condition to hold for all the i's. Right? So that's really all we're trying to do. So in this case, what you would have is the equation for the ith one would look like BI, the power for the ith transmitter PI times GII is the gain for that link, divided by the sum over all the j not equal to I of PJI. So this is the, PJ times GJI. So this is every other transmitter and its cross gain to your receiver. Right? So all of this is interference. Plus the noise of the receiver is bigger than or equal to some theta. Okay? So this is an equation for the ith receiver, but you have n such receivers. So really, we have this equation for all of the possible receivers, because there's n such inequalities. And just as before, we can rewrite these as linear inequalities. So we can rewrite this as PI GII is greater than or equal to theta summation of j not equal to I GJI times PJ plus theta n. And we can, just as before, kind of rewrite this as PIGII minus summation of, for j not equal to I, theta times GJI times PJ. Let's leave the theta n on the right. And so this is, again, not just one inequality, but a whole bunch of them. And if you kind of look at this, you have all of the PI terms. There's P1, P2, P3, all the way up to Pn. And there's one of these for every I, there's such an equation. So what you can imagine you're doing is you're trying to sort of multiply two vectors. Right, so there's this vector P1 through Pn, and there's a set of coefficients that this row vector times this column vector, that's everything here on the left-hand side. Right? Why is that? Because if I have a vector here of size 1 by n, this vector of n by 1, I'll get one number. That number has n terms in it. It's like the first term of this multiplied by the first term of this vector plus the second term of this multiplied by the second term of this vector, and so on. Right? So we're going to write it in vector notation, and we're going to see the left-hand side here as the product of these two vectors. The right-hand side in this case is simply just the number theta n. Right? So what should this vector look like? Well, whatever is pi, the corresponding term over here is going to be GII. That's going to be the ith term. Right? And all of the other terms are simply going to look like the jth term over here is going to look like so the jth term is going to look like negative theta times GJI. Okay. So and we want this to be greater than equal to. So, so if I look at one of these equations, I can rewrite it as this vector of basically negative theta g1i, negative theta g2i, dot, 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 and then this ith term looks different. It just has a gii, and so on. Okay. So that's what this vector is. So this is a description of what's happening for the ith equation. And I can stack up all of my n equations on top of each other. Every equation basically is giving me a different vector of coefficients here, right? The right-hand side in every case will just be theta n. The thing that they're all multiplying, every such inequality is going to have all of the values from P1 through Pn in it. So basically I can take these n inequalities and express them in the form of matrix inequality that looks as follows. Sort of element-wise bigger than a vector we're going to call B. So A is a matrix that's of size n by n. And P is the vector P1 through Pn. And B is the vector that simply has theta n in every entry. Okay. And the matrix A is such that Aij equals Gii for j equal to I and negative Gji times theta for j not equal to I. Okay, so this matrix A that we're talking about is simply a bunch of these terms. And on the ith row, the diagonal element is the one that's Gii. All of the other elements are negative theta times Gji. So that's what this is. Okay. So basically, the entire set of SNR conditions that we're talking about can be written as this what's called a matrix inequality. Okay. And so this matrix inequality and this sort of element-wise, right? We don't really define greater than equal to for vectors. B is actually a vector. But what we're saying is every element in this, so this is an n by n times n by 1, so this whole thing gives you n by 1 vector, and this is an n by 1 vector. So this is a vector on the left-hand side, a vector on the right-hand side. There's no such thing as a vector is greater than another vector, but you can, what we really want to say is every element is greater than equal to, right? Because that's the SNR. So if we can find a solution to this linear matrix inequality, so this is called linear then we're good, because that's the goal. And in the special case of two links, we basically found that there's a condition under which you're able to find a solution. Right? And similarly, for this linear matrix inequality, also there's going to be a condition under which there is a solution. So for example, if you're actually trying to find a set of powers such that you can actually get them to be equal, then it would be a linear equation. We would actually have this type of a condition. How would you solve this linear equation? What do we need in order to solve this equation? So when, actually, so what we want to try and figure out is when can we solve this condition. So A is a square matrix, it's n by n. This is an n by 1, and this is n by 1 vector.
When A has a inverse?
when A is invertible, right? And so in particular, if A is invertible, then you can take this matrix equation, you can write it as, so this is just the identity matrix, and so you just get the vector P equals A inverse B. Right? So this would be the solution. So you can find a set of powers that satisfies these with equality. In our two-user case, this was like the intersection point. It was like the minimum power solution, right? And in the two-user case, we found there are conditions under which you have a solution. It turns out that was exactly the invertibility of a 2-by-2 matrix. So in that case, the problem was simpler, and we could work it out. So let's see that condition. But in general, if you write this A matrix, you know all the gain terms. You can write them as a matrix. If that matrix has an inverse, then there is a power control solution where all of the nodes can be allocated power such that they all just meet the threshold. And in fact, then there's also solutions where they'll exceed that threshold. So, but you need this condition of invertibility of the A matrix. So for the 2-by-2 case that we did before, which should only be a special case for n by n, let's just see what the invertibility condition meant. That matrix A is very easy to write down. The diagonal terms we're saying are GII, so G11 and G22. And the other terms are negative GJI, so G21 theta, and negative G12 theta. Right, so this was the matrix in that case. And if you want to check if a 2-by-2 matrix is invertible, what do we check typically? We look at its determinant, and you want to make sure that the determinant is not 0. If it's 0, then it's not invertible. So what's the determinant of this matrix? The product of these two, which is G12, sorry, G21 times theta square. Okay. So we would want that this determinant is actually positive, right? Yeah, we actually want, we also have the condition we don't want the powers to be negative. So we actually want this condition to be greater than 0, or greater than equal to 0, which is the condition we had before when we were talking about this. So, right. Do you remember when we worked with the slopes and we said this is the region we want? The only way in which that there was an intersection region where both receivers would be happy we derived was this condition. In fact, that's exactly the condition for this matrix to have an inverse. But the generalization now is very powerful. It doesn't require us to draw lines and look at slopes, although really if you look at it geometrically, we're kind of doing that, but in sort of higher dimensions. We're looking at hyperplanes and looking at conditions for these hyperplanes to intersect in such a way that they have solutions. But the solution now is sort of general. We have a test for if I give you n links, can I schedule them all in the same channel at the same time by allocating them different power levels so that they're all happy? Right? So that's really what this test allows us to check. And if it satisfies it, it even gives you a particular solution where they satisfy that condition with equality, which is this particular power vector. Right? So at this power vector, you will guarantee that they satisfy all the SNR thresholds with equality. It's like that minimum power point we found for the two-user case. So this gives us a test for if all n links can be scheduled together. Okay. And 2, if so, a power vector that guarantees all SINR values are met with equality, right? There's a very simple thing you can do. If for any reason you want to satisfy this not with equality, but with an inequality, like you want it to be strictly greater than, where did the equation, yeah, here. So this gives us a solution at which all of the SNR is exactly equal to theta. If you want to find a solution where all of the SNR is a little bit above theta, you could just add some epsilon to the theta, right? And solve this equality. That would give you a power vector which would be feasible in a way that all of them are strictly greater. So, so the fact that we're doing it for equality is doesn't lose us any generality. So, okay, so this tells us if they can be scheduled and if they can be what the power level should be, right? But what if the answer is no to the first question? So I give you n links. So you have some region, and there's a bunch of links. Okay, we want to schedule them, so we try to do this power control. And in order to do the power control, we first test by figuring out the A matrix, checking if it has a determinant, if it that's not zero, and if you can find a solution, then and if it is invertible, you can find a solution. So this will give you the solution, right? But in our problem, there is no guarantee that this test will be satisfied with a yes answer. That gain matrix that we have, the A matrix, might not have a solution. May not be invertible, sorry. The matrix A may not be invertible. So if it's not invertible, what could we do? So I have a certain number of links, I want to schedule, I look at the matrix A that I form with them, and the answer comes out to be, no, you can't. So what do you do then? Reduce the number of links, right? So if the problem is that this is too many links to schedule together, you're going to have to kick out some of the links. So what people often do in this case is break up the problem into two steps. First, do this test and see if you can schedule all of them. And if you can't, then find some way to identify links that, if you remove those links, the rest of them might be more likely to be schedulable. And intuitively, it's the links that are somehow causing the most interference to others that are the problematic links in your set. So there are algorithms people develop where they sort of iteratively look at your set, identify a link that's causing a lot of trouble to the other links, basically has high gains to the other links and has a low gain within itself. And if you remove that and try to schedule the other links, you have a better chance of being able to satisfy the condition, right? And if that doesn't work, you kick out another link and so on. So it turns out that that problem of scheduling and identifying, for example, so if you kick them out to not schedule them, you may need to schedule them later. And so you can formulate a problem that says, what's the minimum number of time steps in which I can schedule my n links? Such that in every one of those slots, the matrix A that I get is invertible, right? So this problem turns out to be computationally very difficult. It's in a class of problems known as NP-hard. So there's no single algorithm that's both efficient and guaranteed to be optimal. So people typically come up with heuristics like a greedy approach to try and do that scheduling. So, and we'll come back to that topic a little bit later when we talk about scheduled access. But at this point, you should be aware that it is possible for that test to fail. And if that test fails, it means you have to change the set of links that you're trying to schedule. You just simply can't do it with that particular set of n. I mean, in the special case of just two links, if you have two links and you cannot schedule them together, the condition doesn't work, then you simply have to schedule them one by one, right? So then it's kind of easy to see you must separate them. But if you have any number of, arbitrary number of links, it's a little trickier because it's not clear how should I split them. Even if I was able to do them in two successive times, the number of possible ways in which I can split n links into two possible times is exponentially large. It's 2 to the n possible partitions of the set of n links into two groups, right? And so brute force techniques typically will be inefficient, and techniques that are efficient, it turns out, can guarantee that you'll get the optimal answer. So that's to kind of close off that topic. So I forgot to do this generalization, but. So this particular problem of power control is used in CDMA networks. It turns out that even if we allocate, so imagine these transmitters and receivers are different base stations and mobile devices, or mobile devices and base stations. then nearby base stations might be using the exact same frequency, but allocating different codes to the different users. And on the codes that they're allocated, they'll have a certain gain to their receiver, but the code that a different link is allocated may not be 100% orthogonal, may not be perfectly orthogonal to the code that the first transmitter is using. So this receiver will receive a little bit of the signal kind of, if you will, leaking through the interfering code. Even if it's been allocated a different code, it's not perfectly orthogonal. So some of that interferes with your transmission. And so in CDMA, typically base stations periodically measure the gain conditions and tell the mobile nodes what power level to transmit their data at. So there's actually an online power control mechanism that's part of the operation of CDMA systems. Okay, and that's sometimes referred to as it's called the near-far problem. So the idea is that if you have a transmitter that is close to this receiver, but its own transmitter is far away, so maybe this is its receiver, this is some other transmitter, even if this transmitter is not using the code that the receiver is expecting, because these codes are not perfectly orthogonal, enough of the signal can leak through that this interference might be stronger than the signal that you're getting. And so the only way to adjust for that is to change the power levels. So maybe this transmitter, because of its proximity, needs to reduce its power level, and maybe this transmitter needs to increase its power level so that the SINR of this receiver is the right value. And so the problem that we just talked about is actually used in real cellular systems to sort out this problem. Right? So there, all of the links are technically in the same channel, even though they're using different codes. And the cross correlation between the codes kind of determines, in addition to the distances, determines what the cross gains look like. So going back to random access. So we started by talking about slotted aloha, where you have n nodes, each transmits at each slot with probability p. Okay. And then in the last class, we started talking about something that I call PCSMA, that in the literature is also called, and I think even in your homework assignments, I refer to it as P persistent CSMA. And I said that we can think of it as a generalization of slotted aloha in which we're separating out contention slots from transmission and collision slots. So so contention slots of small duration delta, and then successful packets take some time TS, and collisions last some other time TC. And in general, this is how these different times are related to each other. And the special case where these are all equal to each other is slotted aloha. But the difference in PCSMA for a general range of values for TS and TC and delta is that now your contention is very small. If somebody wins the contention and are successfully transmitting, they can occupy the channel for a longer period of time. While they're occupying the channel, there's no more contention. And the reason there's no more contention while they're occupying the channel is that every sender will first check the channel before it transmits. Okay? So CSMA, the phrase CSMA, it refers to, the abbreviation refers to carrier sense, medium access. So the carrier sensing part is what is ensuring that when you're transmitting a packet for a long period of time, you don't need to have any contention periods embedded within that. Similarly, the collision periods are assumed to also be free of any additional contention. If two nodes started to transmit at the same time during the contention period, once they start to transmit, nobody else will be contending because they'll sense the channel to be busy. And I mentioned that if you don't do anything, you can assume that the collision time and the successful time are the same. It's just however long it takes to send the packet. But in the case of RTS-CTS, which we'll talk a little bit more about, TC might be actually smaller than TS because you first send out an RTS-CTS packet. If that collision happens, you can detect that before you start sending the full packet. And so in some cases, you can actually model the collision time to be shorter than the successful time. And what we showed was that the expected throughput can be modeled by the kind of expected success duration per epoch over the expected epoch duration. Okay. So for PCSMA, in general, the expected success duration is the probability that it's successful times the success duration. And the probability of success is n times p 1 minus p to the n minus 1 times ts. That's what goes in the numerator. And then in the denominator, we have all of the three possibilities. It will last a duration delta with probability 1 minus p to the n, in which none of them transmit. And the epoch will last this duration if it's successful. And it will last sort of 1 minus those two probabilities. With 1 minus those two probabilities, it's going to last a duration Tc. So this is the expression for the expected throughput. So it definitely looks like quite a handful compared to the simple expression we had for slotted aloha, which really was just this, right? And we can see why the equation in that case boils to what we had before, because if delta equals Ts equals Tc, then you can pull that common slot duration out. All of these probabilities add up to 1. That slot duration cancels with what you have in the numerator, and you're just left with np 1 minus p to the n minus 1. Right? So which is the equation we had before. And then we kind of plotted this, and we saw that so long as the success time is bigger than the idle time, this expected throughput is often very high, right? Even 90% or higher. And then we talked about PI CSMA, in which we looked at sort of the throughput region. And really all I said about it is that similar to what we have in slotted aloha, there is a possibility of giving different users different access probabilities so that some users get a higher throughput than others. And we gave kind of a condition for being on the boundary of this throughput region, right? So today what I want to do is relate this p-persistent CSMA to the CSMA that's used in 802.11. And of course, all of us are familiar with 802.11 because that's our predominant way of accessing wireless data on our laptops and our cell phones when we're in range of access points and so on. So let's take a short detour from our math to kind of look at the standard for 802.11 briefly and kind of understand that better. So could I have this computer projected, please? Okay. So I have it open just to the Wikipedia page on 802.11, so it's nothing fancy here. But I thought, given what we've discussed in the class, we'll be able to make sense of a lot of things that are described here about these standards. So the first thing to know is that it is an IEEE standard, and a lot of networking protocols have to be standardized because you want different vendors to be able to interoperate with each other. So if I buy a Wi-Fi card from one vendor versus another, I buy my router from a different vendor, all of these have to work with each other. So having a common standard allows different vendors to be able to sell a product that works with others. And especially when you talk about networking, that's always been really central to the way they operate. Within the 82.11 standard itself, there's a number of different variants, as you can see here, over the years. From the earliest 82.11, 1997, which I can't believe I'm old enough to have seen when it first showed up in my undergrad days, and was literally like we were one of the first people to test them out in a college environment. Two variants of 82.11 that are deployed for a number of different applications. So if you kind of look at all of these standards for 82.11, starting from the first one, a couple of things to notice. First is that the frequency band in which it operates is either the 2.4 gigahertz band or the 5 gigahertz band. And the reason that these two bands are chosen generally is that these are the two ISM bands which are unlicensed. So unlike cellular networks, Wi-Fi networks operate in an unlicensed band, which means that you don't need a license from the government, from FCC, in order to operate in that band, and nor do you have an exclusive right to use that frequency. This is the same frequency that is used by Bluetooth. It's the same frequency spectrum that's used by Zigbee. You get all kinds of other devices that are in the same spectrum, so there's a lot of interference between them. So in some sense, it's a best effort spectrum. You don't have a guarantee that you will be able to get exclusive use over that spectrum. But amazingly, it turns out to be a very efficient use of that spectrum to run these data services on. So the other thing to notice is that the data rates have gotten higher and higher over the years. So if you look at, for example, many of us now have like an 82.11n router. They're really promising, anywhere between tens of megabits per second to even hundreds of megabits per second, right? So that's a far cry from the earliest 1 megabit per second system that was on the market. Other things that we've talked about in this class, we've talked about different ways of modulating or representing the data digitally. The earliest versions of 82.11 had spread spectrum. So this is direct sequence spread spectrum and frequency hopping spread spectrum. More recent versions typically have OFDM, because if you remember, the higher you go up in data rates, the more the problem of intersymbol interference shows up. And OFDM offers a way out of that problem by breaking your data stream into multiple OFDM streams, each of which has a longer symbol duration, right? And so you suffer less from the intersymbol interference problem with OFDM systems. The number of OFDM carriers might be a little different across each of these standards. I don't have it off the top of my head. We can see if it comes to it. The other thing that you notice, we talked about Mimo. Up until before the 82.11n standard, there was no Mimo in 82.11. But after that, you're seeing a number of Mimo streams show up. So 4 for 82.11n. There's another standard called AC, which offers 8 Mimo streams. So this is sort of the setting where you're trying to get throughput improvements by using Mimo. So we talked about the diversity multiplexing trade-off. Here, the maximum multiplexing gain you can get is a factor of 4, right, by having this, if you had 4x4 Mimo stream. There are some subtle differences also in the range that they're able to provide. Intuitively, there's only 2 ways in which you can get a range improvement. One way to get a range improvement is to increase the power level. The other is to improve the efficiency or reduce the error rates, right? So both of those are factors that will be contributing to the increase in range. So sort of some of the concepts we've talked about in the class will show up as you look at these. If you look at the 82.11a, already started to use OFDM. I don't know if it talks about the number of OFDM carriers here. Yeah. This is 82.11g, which for a while you sort of had A/G or B/G cards. So here is a graphical representation of those Wi-Fi channels in the 2.4 gigahertz band. So the entire spectrum is 2.4 gigahertz, but each channel that the Wi-Fi might be placed on is only 22 megahertz within that larger band. And which particular channel your router is set up at is either the default value that it ships with, or you can control it manually. Typically, you can configure what channel it's located on. I think some of the recent routers actually have a setup phase where they look around and see which channel is freer and then kind of fix themselves on that channel, but they don't periodically change that necessarily after that point. If you start to look at the spectrum usage these days in urban environments, there's lots of Wi-Fi usage. You'll find that a lot of them are sort of clustered in either 1 or 6 or 12. Which are, or 11, I think, which are sort of the default channel settings that the vendors provide. And so if you kind of look around, you might actually find a slightly better frequency channel to set up a particular box on. Let's see if there's anything else here. So the standard, besides talking about medium access and the physical layer, parameter also has a lot of details about how the authentication process works. So how does your card register with an access point? And all of us these days use encryption, set up a password on our access points. So part of the specifications in these standards is detailing how that whole process works. So we're not getting into those details, but if you're interested, certainly there's information about that out there. So the other standard of 82.11, related to 82.11 I wanted to mention is 82.11e. So in the original 82.11, there is a, in the medium access, there's the DCF and PCF. We're going to talk even today as we continue to talk about CSMA in 82.11. We'll be focusing on something called the distributed coordination function. The difference between DCF and PCF is that in DCF, the senders are not coordinating with each other. There's no scheduling. There is no signaling from the access point about which node is allowed to talk when. Whereas in PCF, the access point can actually control when individual devices are allowed to speak. And so this is sort of better, would be more useful if you have a very structured data environment, whereas DCF is really what we use for most of our best effort, bursty type of traffic. And so the CSMA CA that we're going to be talking about will really be the 82.11 DCF. Okay. In fact, as this Wikipedia article points out, the PCF mode is considered optional, and very few access points or Wi-Fi adapters actually implement it. So it turns out not even to be widely used in practice. And we'll talk about RTS, CTS as well. So the 82.11e does something that's related to our discussion about PI CSMA. So we said that if you want different users or different applications to get different throughputs, then they should access the channel with different probabilities, right? And I mentioned last time that in 802.11, these probabilities, the access probabilities, are not chosen from a geometric, are not chosen as independent at each time, which would be equivalent to a geometric distribution, but instead the access is generated randomly from a uniform distribution, where you have the sender pick a random number from 0 to a maximum window size, and counts down from there. When it hits 0, then it transmits, right? And so depending on how long that window size is, that's going to affect how frequently you will try to access the channel. So if that window size is small, you'll count down quickly and try to access again, right? So if this was the P-persistent CSMA, having a small congestion window would be equivalent to having a high or low probability. high probabilities, right? So small congestion window means you access the channel more frequently. If it was a P persistent CSMA, you would access it frequently with a higher P, right? So likewise, in the other direction, if you have a high congestion window, then your random counter, the backoff counter that you pick, might take a long time to count down to 0. That's equivalent to or analogous to having a low access probability. So in the 82.11 system, where we don't use probabilities, but rather these congestion windows, having a small congestion window, or not congestion window, sorry, collision window, contention window. Contention window. If it's small, that's like being really aggressive. If it's large, it's like being not so aggressive. So traffic that's higher priority, would we want to give it a high contention window or a small contention window size? Smaller, right? And so that's exactly what 82.11e does. So it creates a number of what they call access categories. And the access category is something that's sort of application dependent. So there's an access category for background traffic, best effort traffic, video traffic, 2 versions of video traffic, and sort of legacy DCF, which is the standard 82.11. And you can see that as you go from the standard 82.11 or background traffic to the video traffic, the maximum congestion window goes from being 1023 to just 15 or even 7. And the minimum goes from 15 to 7 or even 3. Right? So these two, and in fact, if you look at this one, oh, sorry, voice. Why did I say video? This is video and this is voice. So for voice, they're giving the highest priority, the next to video, and then the background. So this access category has the shortest contention windows and therefore the highest probabilities of access. So they've kind of statically configured these different access categories to have different probabilities, if you will, right, or different frequencies of access. So that idea of having different performance for different users is actually captured in the 82.11e standard. As a standard, it's not very widely adopted, I must add. I don't think our standard cards can switch between these. But you can certainly program in a similar access priority capability into your Wi-Fi system if you have access to the Mac layer parameters. So for example, in Linux, there are Wi-Fi drivers that actually allow you to change the CSMA parameters. And so you can change the contention window to be shorter for higher priority applications or nodes. So I think that's really all I wanted to say about the standards in general. So what we're going to talk about now is how do we analyze the saturation throughput, not of CSMA in the simple PCSMA model, but for the IEEE 82.11's version of CSMA. So the analysis that we're going to talk about came directly from this paper in 1998 by Giuseppe Bianchi. And he was the first to kind of look at how that standard, while it was being proposed, like 98 was very close to when it was being standardized. And kind of how do you mathematically explain what throughput you're going to get with the standard, right? So here's a kind of basic picture of what the standard looks like as far as the CSMA behavior goes. So this is the each packet. So the packet has a PHY header, a MAC layer header, the payload. After each packet, there's a short interframe spacing. Not explained here in any detail. And then there's an acknowledgement period where you can hear back that the packet was received. After that, there's another period known as DIFS, which stands for Distributed Interframe Spacing. And basically, when you have a packet descend, first you just monitor the channel for this diffs period. That's the period of time in which you're trying to check if there's something on the channel or not. And immediately after this diffs period, you have a slot time. And the station, when that slot time starts, you're allowed to start transmitting. So this is like our, for the PCSMA where we talked about it, this is the contention slot. And this is when you're allowed to try and transmit. And this after this slot period, you're on to the next slot period if there is no transmission, and so on. So here's the first transmission from some node, A. Then after a period of diffs, the next slot period started. Nobody transmitted in this period, so the next slot period started. Nobody transmitted in this period, so the next slot period started, and so on. And then eventually, station B started to transmit. When station B starts to transmit, station A kind of freezes its back-off timer. So at this point, after it transmitted, it picked a random number from a uniform generator and has been counting it down. It had a timer of 9 that it chose randomly. So it's going to wait 9 empty slot periods before it will try to transmit again. And during this time that the station B transmitted, this is like that TS period we talked about. So starting from the beginning of 5 to the end of this diffs, this is like the period of time that the successful transmission from B is happening. This is like the TS period. And after that, when the channel is free again, the station B presumably also picked another back-off number. Whatever that number was happens to be long enough that nobody transmitted at this slot or this slot. When it comes to the end of this slot or the beginning of the next one is when station A's timer has counted down to 0 and it's ready to transmit. So it goes ahead and transmits, right? And likewise, whenever station B finished transmitting, it would have picked another back-off window and waited till it's ready to send again, and then it's going to try. Okay, so because you're always checking the channels, you're doing the carrier sense. When station B is transmitting during this period, station A will not transmit, and so this whole thing will count as sort of one slot period. So the next slot will resume only after the diffs ends after this transmission. Okay. So the backoff period itself, so every time you send a packet, if you have another packet to send, that backoff period, I said, is chosen uniformly, and it's chosen in this range between 0 and W minus 1, where W is the current contention window, right? And what I mentioned before is that in 82.11, they have this notion of stages, and you will double every time you're experiencing a collision. So for example, I think we might be able to see in the 82.11 standard, we can maybe try and infer what some of these collision windows might be, how many stages you might have. So for example, this one is going from 15 to 1023, so think of this as like 16. So after every collision, it's going to double. So it'll go from 16 to 32 to 64 to 128 to 256 to 512 to 1024. When it reaches that maximum congestion window, it's not going to keep doubling anymore. So after that point, it's kind of stopped. So in this particular case, the number of times it doubled would be the number of stages that you have. So for example, what do we have? So we had 16, 32. So in this particular example, there were, could I get the overhead camera, please? So in this particular example, on my viewer over here as well, yeah, thanks. So in this particular example, they have the first stage is this one, and the mth stage is this one. So you have 1, 2, 3, 4, 5, 6, 7 stages, right? Each time you're transmitting a packet, initially you start with that first stage, and you pick a random number from 0 to the window that you have here, minus 1. So we call this, I think, W0. And this is sort of WM. This is W1, W2, W3, W4, W5. Okay. So if then I should call this M minus 1, I guess. So this is W6 for us. Okay. So when you first begin, you're picking a random number between 0 and 15. You send a packet. If when you send that packet, everything is fine, then you pick another number from 0 to 15 and repeat. But if when you're sending that packet, you experience a collision, which in this case is detected by just not getting the ACK back, then you will double your contention window to 32. Now you'll pick a random number from 0 to 31, right? And then you count down. Now when you transmit, if everything is fine, the next time you'll go back to the first stage. But if it's a collision, you'll move to the next stage. Now you pick a random number from 0 to 63. Right? Again, if you have a collision, you go and so on and so forth. So the only reason for you to walk up all the way to the other end of this is if you're experiencing collisions at every stage so far. And then you'll keep doubling. If you're at the last stage, there's no more doubling. Now if you're experiencing a collision, you still pick a random number from 0 to 1 or 2, 3. You don't double anymore. Because that's what's happening here. So if we kind of look at the combination of the back-off counter and stage number, so you can kind of view this as a state for the protocol. In these 82.11 standards. So let's take a toy example just to work with it, where we're going to say the W0 is just 2 and the number of stages is, let's take 3 stages. Okay. So what does that look like? So if you in order. Yeah. So if you take in the 0th stage, you have only 2 possibilities for the back-off counter. It could be either at 0 or it could be at 1. And so let's call this 0, 0 and this 0, 1. So we're indexing by, let's call it I, j, where I is the stage number and j is the back-off value. After that, if it went to the second stage, the possible values that the back-off could take on in the stage are these 4 values. Okay. And then the last stage, there's sort of 8 possible values it could take on. So the way these states transition, if you have a certain back-off value at the next time step, you're going to just decrement it by 1. Okay? So the probability 1 for any state where the back-off counter is bigger than 1, at the next time step, it's going to be still in the same stage with a back-off counter 1 less. Right? So the transitions from all of these states that are to the right is simply with probability 1, you move to the left. And then when you reach any of the stages on the left-hand side, you're basically, your back-off counter has hit 0. What should you do? So you're a node, you picked a back-off counter. You kept decrementing it every time either that the channel was free or at the end of the disk period if the channel was busy. And then it's finally hit 0. What should you do now? Transmit, right? So after this, they're going to transmit. So all of these cases are sort of transmit states. And if they transmit, one of 2 things will happen. With a certain probability, that transmission will be successful, in which case you will come back to the first stage or the 0th stage. And if it's unsuccessful, meaning there's a collision, you'll go to the next stage. Right? If you're in either of these 2 stages, or if you're in this stage, you'll stay in the same stage. So with probability of success, which we're going to call, let me use the notation in that book. So I'm going to in that paper. So we're going to call the probability of collision to be P. In which case the probability of success is 1 minus P. So with probability 1 minus P, you're going to pick a new counter, and you're going to pick randomly between these two values. And so with some probability, you'll just pick 0. With some probability, you'll pick 1. That's exactly half for each of these two cases. So each of these two arrows transitioning out from here will have a probability 1 minus P over 2. Okay, there's 1 minus P over 2 here, 1 minus P over 2 here. Together, they add up to 1 minus P. They're all the cases that the transmission was successful. If you have a collision, what you end up doing is you go to one of these states. Right? And that happens with probability P that you'll go to one of these states. And any one of them you'll go to with equal probability because it's a uniform generator. So this is probability P fourth, P over 4, P over 4, P over 4. Right. Similarly, if you find yourself here with probability 1 minus P over 2, the same probabilities that we had listed here, you would transition to one of the first stage or the 0th stage states. And with probability P over 8, you might end up at one of these stages. Right, so for all of these transitions, you have a probability P over 8 of making those transitions and ending up here. And similarly here, with probability 1 minus P, you have a success, and with 1 minus P over 2, you'll end up here or here. Or with probability P, there's a collision, and you might end up at any one of these states at the next time step as you pick a random counter again. And these are all also probability P over 8, right, for all of these. Okay. So this whole thing we have is basically a Markov chain. It's a Markov chain because we have a set of states and probabilities of transitioning between these states. And it's a discrete time Markov chain. It's a finite state Markov chain. And we know all of the probabilities in it. We know all of the states that we're in. Right? So this is the type of Markov chain we know what to do with. This is the probabilities we just described tells us the entire P matrix for that Markov chain. We know how to evaluate in particular its steady state behavior. So we can say in steady state, if I run this Markov chain, over a long period of time, what's the probability I'll find myself at different states? Right? So here's the question. What state will tell us about the time that we spend successfully, not even successfully, which state tells us about the time we're spending doing transmissions? So if I want to figure out my long-term frequency of transmission, right, analyzing which set of probabilities or which set of states would be useful? Which state? Steady state, but among the states that we listed here, these circles are all states, which state is going to be the one that's most relevant to transmissions? This one, and this one, and this one. So all of these states over here are transmission states, right? So if I know how much time I spend in these states, together they tell me how much time I'm spending transmitting. Multiplied by the success probability, it's telling me the time I'm spending sending successfully, right? So in fact, 1 minus P times the steady state probability of being in these states is my probability of successfully transmitting. Okay. And so analyzing this chain will give me the probability of successful transmissions and will give me a way to kind of analyze the throughput of the system. So that's sort of the key idea. So in the paper which you're going to get to read, the notation that's being used is as follows. So the state is described as a pair. I called it IJ in the paper. They call it STBT. And this captures the stage, which goes from 0 to M. And BT goes from anywhere from 0 to whatever it's called, WS minus 1. Right? Whatever stage you're in, minus 1. That's all the values that this would take on. And the steady state probabilities are referred to as B I comma K of being in state basically S equal to I, B equal to K. And if you take this Markov chain, you can solve for that steady state probability by, for example, applying the global balance equations, or even the long way around would be to just write out the full P matrix, write out the relationship that the steady state probabilities have with the P matrix, which is that, if you remember, right, there's this as well as the fact that well, the sum of all the pi i's must add up to 1. So together, these things help you figure out what the steady state probabilities are, right? Also, hopefully in 503, you saw some other ways of actually deriving the steady state probabilities using the global balance equations and so on. So if you actually run through all of that math, what the paper shows is that you can essentially come up with an expression for B00. So I'm going to skip the details of the derivation here. So can show for any M and also they made some assumption about W. So what is W? Yeah, and initial window size W, number of users. Oh, number of users doesn't show up here. And collision probability, and we'll come back to how do you figure out this collision probability in a second. So if you know M is the number of stages, W is your initial window size, which we were calling W0, and the collision probability, which showed up in this chain, these P's. If you know all of those things, that you can prove B00, which is the steady state probability of being in this particular state, is something that you can derive in closed form to be this equation. Times 1 minus. Okay. So don't worry about the details of the particular equation. I mean, it is clearly complicated, not something that you could see at a glance how it was derived. The details are in the paper, which you'll get to read. But the main takeaway is that these three parameters, the number of stages, the initial back-off window, and the collision probability, all of those show up in this expression. If you tell me what those three numbers are, I can tell you what is the steady state probability of spending for this Markov chain of being at state 00. Moreover, they prove that for any BI0, the probability could be written as P to the I B00. So we know the probability for the state 0, 0, and for any other state, for any other stage, comma 0, it's simply p to the I times b 0, 0. Okay. You can kind of see intuitively how this is happening, because at the 0th stage, it's just p to the 0, so just b 0, 0. At the first stage, it's with probability p times b 0, 0. So it's like the probability of seeing a collision, you're at the second stage. Probability of 2 collisions, you're at the third stage, and so on. Right? So this is basically multiplying a factor of p for every additional stage, and that p is exactly the probability of collision. Okay. So at least intuitively you can see why this expression might make sense. So the derivation of the steady state probabilities, which we've skipped, turns out to be tractable for this problem because of certain regularities about the system. I mean, in particular, if you notice, there's a whole bunch of edges here which just have probability 1. That really simplifies the calculation of the steady state probabilities, it turns out. And all of these transition probabilities are all the same value. Right? So there's a lot of regular structure in this P matrix which allows there to be a simple tractable expression, maybe not simple, but at least a tractable closed form expression for the steady state probabilities. Right? So this is good. So now we know for any one of those states what's the probability you're spending time there, right? Which means that if I think of every time step as a time that I'm spending at one of these states, it's giving me the long-term proportion of those discrete time steps that I'm spending doing transmission. If I simply add up all of these over I, going from 0 to m, this is the steady state probability of being in a transmission state. So what is this? We actually have the equation. So we have I goes from 0 to m, p to the I b 0, 0. Okay. And the paper says that this is equal to b00 over 1 minus p, but really I think that's more of an approximation because this is a geometric series with a finite number of terms, so there's actually some other components there, but roughly speaking, it's like b00 over 1 minus p. And we know the expression for b00, so divide by 1 minus p, simply get rid of this term over here. So it's just, so this whole thing simplifies, and we're going to call this expression tau. So they give an expression for tau to be 2 times 1 minus 2p over 1 minus 2p times w plus 1 plus pw times 1 minus 2p to the... Okay. And so this tau is, as we said, a steady state probability that and then finally they say we can actually relate this tau back to the p. So right now, I said we can derive these probabilities if we know m, w, and p, right? So m and w we will know because those are specified by the standard. Like if I use 82.11, I can check what is the minimum contention window, what is the number of stages, so I know m and w. Those are given to me. P is not a given. P clearly depends on the system itself. Right? So what's the collision probability? It should depend on who else is around you, how many of nodes are around you, are they transmitting, and so on. Right? So intuitively, the actual medium axis is going to determine the collision probability. If you're the only one in that medium, the collision probability is 0. Right? And I'm actually starting to wonder what will happen to this equation if p is 0. So let's just take a quick look. So if p is 0, in this equation, these two terms become 1. So you have 2. This will be 1 minus, this is just 1. This becomes 1. This term disappears. So you end up with, if p equals 0, b0, 0 equals 2 over w plus 1. And in fact, this will become tau because there'll be no collisions for you to go to any of the other states. And so the probability that you'll transmit would simply be 2 over w plus 1 if you're the only one in that area, which makes sense because you have a certain window size, and on average, once roughly half of that window size is what it takes you on average to wait to transmit. So roughly 1 over that, which is 2 over w, there's a plus 1 here, is the probability that you'll transmit, right? So if p was 0, this is what it would be. But in general, p might be higher. Intuitively, it's going to be higher if there's more than one transmitter. So what is that value? Well, we know that from the fact that all of the transmissions, if we assume that this probability p, so what we're going to do now is use a PCSMA model to determine relation between tau and p. So what I mean by a PCSMA model is that we've taken the 82.11 CSMA, which has these uniform windows from which we're drawing the back-off counter, counting down, and then sending. But we're taking that process, that random process, which is a Markov chain, and we're saying we'll take all of that and we'll look at the steady-state probabilities. And we'll pretend that what this node is doing is that every time slot with this probability it's going to try to transmit. Okay? It's like we're taking an 82.11 device and we're pretending it's a PCSMA device. And given W, given M, we're going to talk about P, but given those values, you can figure out what is the probability that you'll transmit. And if you know the probability that you'll transmit, I can infer from that, if I pretend it's a PCSMA system, what's the probability that there will be a collision. Okay. So one subtlety here is that the P that we're talking about is already conditioned on your transmitting. So when we were discussing you transmit here with probability P, there's a collision, and probability 1 minus P, there's no collision. This is already conditioned on when you transmit. Okay? So when we were originally analyzing PCSMA, we said, what's the probability that there's a collision? Is the probability that there's more than one transmitter? Or the probability that there's no one transmitting was like 1 minus P to the n. But now the probability P that we are talking about is a conditional collision probability. So you're going to transmit, for sure. What's the probability that there is a collision? That's basically 1 minus the probability that no one else sends. Because if any of the others is sending at this time, there's going to be a collision, right? So the only way to avoid this collision, so let me put it this way. 1 minus P, which is the success probability, you're going to send for sure. So the only way to guarantee the success is that none of the others transmit. Okay. And we're pretending now that it's a PCSMA system. Everybody is transmitting with probability tau. The probability that none of them transmit is 1 minus tau to the n minus 1. Okay? And the reason it's n minus 1 is that we're already conditioning on the fact that you're transmitting. We're just focusing on the others. Right? And so because of this, you can write P equals 1 minus tau to the n minus 1. Okay? So we've done something that's subtle but very important. What we've done is, first we started with the protocol for 82.11 CSMA, which involves these uniform back-off windows. We modeled it as a Markov chain. We analyzed the Markov chain, derived from it its steady-state probabilities, which gave us tau, right? But tau depends on P, the probability of collision, right? Then separately, we said, if there's going to be some probability with which you transmit, and if we assume that everybody is doing that, independently of you, every other node is also transmitting with the probability tau, then under this sort of modeling, what we're saying is the probability of collision would be 1 minus tau to the n minus 1 when you transmit. Okay. So this first set of equations relates tau as a function of p. This equation relates p as a function of tau. Right? So in this equation, the problem was you might know w, you might know m, but you don't know p. You also don't know tau. So it's like one equation and two unknowns. That's not good. But when we take into account this equation as well, we end up with two equations and two unknowns. Right? So if I call this equation 1, I call this equation 2, then we have two equations. One relates tau to p, the other one relates p to tau. Right? In the first equation, if I know w and m, those are just constants. Then it's just a way of, if I give you different values of p, it would give me different values of tau. Similarly here, for different values of tau, it can give me different values of p. Right? So imagine plotting these two things, right? So you have, I'm not even going to think hard about how these things relate to each other, but intuitively, as you increase the probability that you transmit, you would imagine that the collision probability will go up. So there's some relationship between these two. And with respect to the CSMA analysis, also there's going to be some relationship between tau and p that comes apart. Maybe it looks something like that. That point at which they both intersect, those two curves, that's the combination of tau comma p that satisfies both equations, right? So if you have two equations and two unknowns, you can plot both of those curves. You can see what's the point at which they intersect. And that will give you the solution that we're looking for. So at the end of this, what do we have? So then we know p and tau, actually. So if you know p, what can we do at this point to figure out the throughput of 82.11? If you know tau as well as p. Actually, tau is all we need. We go back to what we did. We go back to this equation over here. So my notation has now changed a little bit. Before, p was the probability with which you access the channel. And in Bianchi's notation, p is the probability of collision. Tau is the probability of accessing the channel. So if I take this equation, replace p with tau, solve this equation, that gives me the mathematical throughput for 82.11 CSMA. So that's basically what Bianchi proposes to do. Substitute tau into the throughput expression for PCSMA, and you get and I'll put this in quotes or parentheses maybe, approximate saturation throughput for IEEE 802.11 CSMA. So one thing to note is that now in this equation we also took into account the number of nodes contending. So in these equations, in order to solve for p and tau, you need to know w, you need to know m, and you need to know n. Right? So overall, this gives a procedure to calculate the throughput given w, m, and n. Okay. So these two are protocol parameters. This is the, if you will, the number of contending nodes. So this is somehow not something that the protocol knows in advance. It doesn't measure this and then decide W and M. W and M are typically specified in the standard. And so for any given value of n, it's going to give a different throughput. And hopefully they chose W and M in such a way that it gives you good throughput for typical values of n. What is the typical value of n? Well, it depends. You know, if you're in a in your home, and it's probably only 2 or 3. There's only the people in your home accessing the access point. If you're in a busy conference room and everybody's on the Wi-Fi, it could be 30, 40, 50. Right? So that n is just a function of how many nodes are accessing the network.
Excuse me, Professor, is your 5-minute warning?
Sure. So what this paper does is it gives you a mathematical way to derive the throughput of the IEEE 802.11 standard. Could I switch to the computer screen, please? So here is the expression in the paper for the expected throughput, and you can see it's basically the expression we've been using. Here, EP is the expected packet transmission duration, and T. So they make a subtle difference here. There, what we were calling TS, some of that portion they count as overhead and some of it as packet. And so there's a subtle difference in the numerator. They're only focusing on the portion of time that the packet is actually being sent, whereas for the TS, they're also using some additional overhead time where the channel might be sensed busy because of a successful transmission. TC is the collision time, just like we had before. PS is the probability that a transmission is successful. And the way they've refactored this equation, sort of, there's a period of time C or psi that's incurred regardless of whether the channel is idle or in collision or in success. So they sort of refactored this equation a little bit. But they give you what the values of TS and TC are for typical original 802.11 standards. So this is the success time includes the header, the actual packet duration, the SIFS time, the delta, the delta is something else, it's a propagation delay, the acknowledgement time, and the diffs, and so on. So all of this is taken into account in the success time, but only this portion of it is what they're counting as the for the throughput. And then for the collision time, they don't take into account some of these other, there's no ACK, for example, so on. So if you have RTS-CTS, the RTS collision time is even smaller. You don't end up waiting for the whole packet. You just wait for an RTS period of time. But in this case, the success time also includes an overhead of RTS, so that's sort of the trade-off there. And then for particular values of these different parameters, for particular values of W and M and number of nodes, which is the x-axis, they're able to derive the saturation throughput and plot it. Okay. And so for your project that we'll assign, you'll basically use this approach to derive the saturation throughput mathematically, and then you'll do the simulation using NS3, and you'll compare those two results, and hopefully you'll find that they match pretty closely. In fact, this figure is already doing that. They're comparing the analysis versus simulation, and they found a pretty good fit. And generally, you do get a very good fit between the two. So I think this analysis is a non-trivial analysis, but hopefully the high-level picture stays with you, which is that by understanding how the 802.11 protocol operates, we can derive a finite state machine that describes it. We can model that finite state machine as a Markov chain, where the probabilities of going between different states depend on the probability of collision. And in order to figure out the probability of collision, we take into account, first, if we knew the probability of collision, we can figure out the probability of transmission, which has to do with being in the transmission state. And then by using a CSMA model, PCSMA model, we can derive the collision probability as a function of those transmission probabilities. And these two equations in two unknowns give us both the collision probability as well as the transmission probability. And when you have the transmission probability, you can calculate, in fact, in this they calculate the success probability, and conditioned on so the probability that you're transmitting is this probability, and the probability that you're successful can then be written out. And so if you know tau, you can figure out the success probability, and that success probability is what you need to plug into the PCSMA equation for saturation throughput. And essentially, this equation is really the same equation we worked with before. Okay. The version of it here looks a little bit more complicated, but actually a little bit simplified even, because they just took that equation that we wrote for the success probability and they just wrote it in here this way. There is one subtlety in that the transmission probabilities here in our case, the success probability was just looking at this portion of it, whereas they're looking at the success conditioned on sending a transmission. So that's why their equation looks a little different. But the net effect of all of this is that you'll get an equation for the throughput, and in order to put in the numbers for how long the transmission period lasts, how long the collision period lasts, how long the header period is, and all of that, they give you kind of numbers, typical numbers for that protocol that you can then substitute in. Okay. That's about it for this lecture. We'll post the project description, and I'm sure as you're going through it, you'll have questions. Feel free to ask the TA and me, and we can clarify. Okay. I think we'll have that posted maybe, if not today, tomorrow, and it'll be due the next Friday. Okay. That's it. Thanks.
This concludes EE 597 with Professor Krishnamachari on Wednesday, June 22nd, 2016.